Okay, so here we are again, and this time we're looking at oxidation states and oxidation numbers. Hopefully you'll remember that we've sort of come across oxidation numbers in the past when we've looked at ionic compounds. If you remember back to when we were naming ionic compounds, we always stated that when we were dealing with metals that could have a variable oxidation state, such as things like copper, we had to state in the name whether it was copper 1 chloride or copper 2 chloride. So that idea that copper 1 chloride would just have the 1 Cl because it was Cu plus 1, whereas copper 2 chloride would be CuCl2. And we would write these as copper and then 1 chloride, or we could write it as copper 2 chloride. And at this stage, we've referred to these as valencies, but really what they are is they're telling us the oxidation state of the copper in that compound, or telling us the oxidation number. Okay, so we need to know the oxidation state, because if we can follow the oxidation states, then we can figure out if redox has actually occurred. So let's figure out how to work these out. So in this video, we're going to look at understanding the difference between oxidation state and oxidation number in terms of terminology. We're going to look at the oxidation state of metals and non-metal elements in ionic and non-ionic compounds and how we work those out. Follow the rules that we're going to establish for oxidation state, for calculating oxidation states for elements that have variable oxidation states. These will primarily be non-metals, but as we've said, we need to work these out for metals as well, particularly those D-block transition metals. And then using those changes in oxidation state to determine if a redox reaction has occurred, or what the oxidation or reduction process is. Okay, so largely oxidation numbers are a construct of chemists that were created to make electron transfer more obvious where it's not really easily seen. So a lot of the reactions that we've looked at so far have been metal displacement reactions or the formation of ionic bonds, and in both of those it's pretty clear when we've got electron transfer occurring. So we can use those rules of oil rig, where oxidation is loss and reduction is gain, to be able to sort of figure out what's going on. Sometimes, particularly when we're looking at the formation of covalent compounds or the change in bonding in covalent compounds, it's not as clear because our electrons aren't really being transferred. All we're really doing is changing the bonding environment. It can be hard to see what's going on with the electrons in terms of redox. So if we look at this combustion reaction of carbon, so something like coal, just pure carbon, reacting with oxygen, okay, to form CO2. This is a redox reaction, and we can see that from the fact that according to our definition of increasing the amount of oxygen in a substance, the carbon is being oxidized here. We're adding oxygen in, okay, but it's incomplete. We're not forming carbon positive ions here. It's a covalent molecule, so we need another way of figuring it out. Because the bonds are polar, the electrons are going to spend more time with the oxygen atoms, and it's a partial, messy kind of situation. In order to deal with that, we need to kind of expand yet again on our definition of redox, and hopefully you're getting an idea here again of that idea of TOK, where our models expand and change as new information comes to light, or perhaps they need to be refined when the previous model doesn't fit the knowledge that we've developed in an area. So oxidation numbers have been created by chemists in order to decide if a redox reaction is occurring. They're defined to enable reactions involving molecules as well as ions to be described as redox reactions. So previously we've just dealt with ions. It's important to realize they have no physical meaning. They don't relate to any physical property in the compound whatsoever. They're just an accounting tool for us to be able to keep track of the electrons. And we have specific rules in order to work them out. So this gives us another way of figuring out if redox reactions have occurred. If the oxidation state changes, so if the oxidation number increases, then we can say that oxidation has occurred. And if we look at something like the example we've seen before, where magnesium solid goes to form magnesium 2 plus 2 electrons. We've seen before that this is an oxidation process that's producing electrons, so the magnesium is losing electrons. But what we're doing is we're going from a charge here of 0, we've referred to these as charges in the past, to a charge of +2. Now in this case we would define this as an oxidation state of +2, and as we can see we've gone from 0 to +2, so we've had an increase in the oxidation number, and this coincides with our classification of it being oxidation. If we look at something like chlorine, say if we're looking at chlorine gas forming a chlorine anion, so 2 chlorine anions, again this is 0, now -1. We can see that the oxidation number has decreased, so this will now be a negative reduction reaction. Okay, so again, it's another way for us to check if we've got redox reactions occurring. So when we follow the oxidation states and reactions, we can see this pattern. This is just another example. So we've got hydrogen gas here with an oxidation state of 0. And then when we form water, oxidation state of hydrogen in this compound is going to be +1. And we'll talk about those rules in a minute. So we see that hydrogen is going from 0 to +1. So the hydrogen is being oxidized, which makes it the reductant. And then our oxygen is actually going from 0 to -2, so the oxidation number has decreased, so it is being reduced, and it is our oxidant that is always reduced. Just a point to note, pretty much most of the time, unless fluorine's hanging around, but if oxygen is present, it will always be the oxidant. Okay, so that gives you a bit of a hint if you're getting stuck with some of these equations. So these are our rules. Essentially, we need to follow these rules. If we follow these rules, we'll always be able to work them out. So let's have a look. Anything in its elemental form, okay, so Cl2, O2, H2, N2, okay, they will always have a oxidation state of 0. Okay, carbon, magnesium, your uncharged solid metals always have a oxidation state of 0. In the case of ions, the oxidation state is always said to be the same as the charge on the ion. So for magnesium 2 plus, the oxidation state would be +2. For bromine going to a bromide anion, the bromide anion will have an oxidation state of -1. So all those common ones, Ag going to Ag plus, it would have an oxidation state of +1 as well. So all those ones where we form an ionic compound, the oxidation state is the same as the charge on the ion. Oxygen is always given a value of -2, okay, when it forms compounds. There are a couple of exceptions, however. One is hydrogen peroxide, so in peroxides where we have H2O2, okay, in this case we have oxygen bonded in a slightly weird arrangement. In this case, like this one, like this Lewis structure, no double bond there, just a single bond. And in this case, oxygen actually has a -1 oxidation state rather than a -2. So peroxide, and the other one where that occurs is in barium oxide. So they're two exceptions that you need to know, but other than that, oxygen is always -2. Hydrogen has a oxidation state of +1 unless it's attached to an incredibly electropositive element, so basically a group 1 metal like sodium or potassium, where we form metal hydrides. And a metal hydride, because the hydrogen will be more electronegative than the metal, it'll form a -1 oxidation state. Then what we really want to look at in this case is how we work out the charges on molecular ions and that, where we don't have a rule. So these are pretty much all our rules. The rest of it we use simple algebra to be able to find out. So if we look at this example here for the permanganate anion, if oxygen is defined as -2, then I have 4 lots of -2, okay, which gives me a total of -8 to the oxygen. I have to add up to have an overall charge the same as the charge that's on the molecule. So in this case, it's -1. So I need to figure out what plus -8 will equal -1, and I can work that out and figure out that it's 7. So in this case, I could write this compound as manganese 7 oxide. Okay, so, and in this case, this is my oxidation number, and the oxidation state would also be +7. They tend to get used interchangeably, but IB does ask us to make a note that the oxidation state is a number together with its sign. So again, we can't imply a positive sign, we have to include it. And so we have the sign and the number, and it shows electron gain or loss during a reaction. So this is just highlighting our exceptions for oxygen. Okay, so we can see here that in the case of when it's bound to fluorine, pretty much anything bound to fluorine is going to be positive because fluorine will be negative. And we can also see that we get variable oxidation states for the nitrogen in different nitrogen compounds. As the bonding changes, the oxidation state will change as well. So this is another example on how to calculate these. If we look at the potassium dichromate, okay, overall we have a 0 charge. Potassium is a group 1 metal. It'll have a positive 1 charge, so our oxidation state will be +1. Our oxidation number of oxygen, we have a rule for that of -2. The oxidation number of chromium, however, is what we don't know. So we can write a simple algebraic expression. We know it's all going to add up to equal 0 because the charge is 0. We'll have 2 lots of potassium, so 2 lots of 1, plus 2 lots of my unknown because of my subscript here, plus 7 lots of -2 is going to equal to 0. So when we add all this up and work it out, we get 2x is equal to +12. So the oxidation number of chromium, or each chromium in this molecule, is +6. So here's a couple of other examples, the last little bit for this video. So now we need to determine the oxidation number of the elements in the following. So if we look at this H2S here, first things first, we look for the ones that we have rules for. We don't have a rule for S, but we do have a rule for hydrogen. Hydrogen, if you remember, is equal to +1. So I'm going to have 2 lots of +1, plus my S is going to equal to 0. So in this case, S must be equal to -2. Okay, so the oxidation state of sulfur in hydrogen sulfide is -2. In H2SO4, I've got the same thing. I have 2 lots of +1 for my hydrogen. I'm going to have my sulfur, which is my unknown, and then I've got 4 lots of -2, which is going to be -8. So in this case, and that's all going to add up to 0. So I've got -8 plus 2, so that gives me -6, which means that S is going to be equal to +6 in this case. So it would have an oxidation state of +6. In the potassium chlorate, we've got a rule for potassium, it's +1. We don't have a rule for chlorine. We do have a rule for oxygen, it says it's -2. So in this case, I've got -8 plus 1, so this gives me -7. So to add up to 0, chlorine must equal to +7 in this case. Hopefully that's making sense. You can always pause the video, go back, have a go at doing these yourself, and then check your answers. So what we've basically done here is we've worked out how to calculate on oxidation states. So once we know the oxidation state on the reactant side and the oxidation state on the product side of our redox pairs, we can look at them. If it increases, we have oxidation. If the oxidation state decreases, then we have reduction. It's one of the few times where we have reduction linked with something that's actually decreasing rather than increasing the amount of hydrogen. So just another example for us to finish up on here. Process of looking at these for reactions, we want to write the oxidation number above each atom. So in this case, carbon will be 0, oxygen is 0. Oxygen, each oxygen is -2, so we always write per atom up here, but overall this will be -4, so carbon must be +4. So the oxidation number of carbon goes from 0 to +4, which means it's increased, so we have oxidation. In the case of the oxidation of oxygen, it goes from 0 to -2, so it decreases and we have reduction. This is a really nice way for us to be able to work out if a redox reaction has occurred. It's a lot cleaner and works a lot more effectively than increasing hydrogen or increasing oxygen. We can follow the oxidation states and we'll always be right for determining our oxidation and reduction processes. So have a go at this one with the oxidation numbers to determine which reactant has been oxidized and which has been reduced. So pause it and then come back and watch the solution. Okay, so hopefully what you realized here is that our sulfur must have an oxidation state of +4. Nitrogen here must also have a +4 because these are going to be -2 each. Sulfur in this case, I have 3 lots of -2, so this must be +6. And then in this case, we have +2. So we can see that the nitrogen here, the NO2 has been reduced because the oxidation number has gone down, and the sulfur dioxide has been oxidized in order to form the SO3. So in this case, okay, our sulfur dioxide acts as our reductant, and NO2 is acting as our oxidant. Okay, just a quick note on disproportionation. We don't see this very often, but essentially just be aware that there are reactions where a single species, usually a decomposition reaction, can undergo both oxidation and reduction. If we look at the hydrogen peroxide example here, oxygen in this case, remember it's our exception, starts at -1. So when it goes to oxygen in water, it becomes -2, so it's reduced. But when it goes to oxygen in oxygen gas, it goes from -1 to 0. So it is oxidized. So just remember that we can have this occurring, and sometimes it's worth it to just check your oxidation numbers and you'll always know. Okay, so that's it for this video. You need to practice calculating oxidation states. There are some example questions in your textbook. I recommend you have a go at those, and we'll look at some trickier ones and things like that. Don't forget to finish your little quiz at the end of this video. It will include what you should be able to do. So that's the calculation of oxidation states or numbers for species in a chemical equation, both just picking them from our rules and calculating them. The changes in oxidation state to determine if a reaction is a redox reaction, and then identifying if it is a reduction process or an oxidation process. Good luck with that, and I'll see you next time in class.